So today is day 6 of vectors, and vectors, so far you've been able to add them. That was super simple. You just add them in column form, just add the numbers, okay? You found a dot product at some point. Do you remember what that was used for? It was in a big old formula finding the what? Yes, finding the angle between two vectors, all right? I think doing one of those would have some value, so I'm going to give you two vectors. You're going to find the angle between those two vectors, okay? But there's a catch. This vector, we know that it's 1, 2, and something. We don't know the third number in it. And let's say that this is the R vector, and I know that this, what does that mean again? The magnitude is 3. Does that mean this is 3? No, that does not mean that is 3. You need to figure out what the third number is here. I'm going to call it an n for right now. Figure out what n has to be, because you know the length of this vector, so you should be able to find its third dimension. All right, it has to do with a squared plus b squared plus c squared equals d squared. All right, then once you figured that out, you'll know what this vector is truly, all three numbers of it. And then you're going to take the Juliet vector, okay, R and J, get where I'm going here. All right, and we're going to see what the angle is between the Romeo vector and the Juliet vector. The Juliet vector is 1, 2, 3. Those two vectors, those are vectors. They go from 0, 0 to that point. That's one way to think of it. What's the angle between them? And it's got a big old formula, and just in case some poor kid has forgotten the formula, and I don't want them to sit there for 10 minutes while you're figuring this out. What is that formula, sir? I'll give you a hint. There's R and J instead of A and B, and it starts with a dot product.
Oh, it's A.
In this case, not A and B.
R.
Mm-hmm.
Then the dot product thing B. No, sorry.
J. There you go. Equals.
Absolute value of R.
Which is also known as the what of R?
I guess the scalar magnitude.
Magnitude. Very good. Okay.
J.
I'm going to not use C. I did that once myself, but I'm going to use theta, just because it's an angle,
Yeah.
and we don't want to call it necessarily C. All right. So, would you please find the angle that's between those two vectors? That is a typical, harder, like R3 level thing you have to know how to do with vectors. Okay? Just so you know, big picture, what we're heading towards today, if you want to know kind of like the goal is to take two vectors and see if they do intersect. And if they intersect, would the vector be heading through the same point at the same time? It's sort of like roads. Do you get if you have two roads, they might have an intersection? But two people that are on those roads aren't necessarily going to hit each other, right? But it's only if they're going through the same intersection at the same time, then they'll hit. So, most of the time, two normal roads that are on the surface of the Earth will intersect at some point, unless they are parallel. But the question would be whether or not a person traveling on those roads, like a vector, happens to be in the same spot at the same time. That's the goal for today. But for right now, just find the angle between these two vectors. I'll pause while you give that a shot. Okay, so that n had to be 2, because 1 squared plus 2 squared plus 2 squared, which would be 1, 4, and 4, all add up to 9, and then you take the square root of that to give you the magnitude. So there we go.
11 divided by 3 square root of 14 is equal to...
But wait, there's more. Excellent. Mr. R in class just said that this is kind of like the ambiguous case triangle that we did a long time ago. You can't tell if that's a 2 or what? A -2. Very good. So, Adam, I'm not going to tell you which one, if I don't tell you which one it is, you'd have to run both scenarios? Because just think about it, would they be different angles? Like one of them might be coming out here and here, and the other would be coming out here and here if they're going opposite directions. They're going to be totally different angles, right? So let's use the positive one just to make your life easier, but I just wanted you to be aware that could have been negative. All right, so we'll use the positive one and find out the angle from there. I'll pause for a second while you finish that. Okay, well, the kids are finishing this one up. I'm going to start with the dot product. The dot product of R and J, that times that, 1. That times that, 4. That times that, 6. 1, 4, and 6 adds up to 11. And you should have had, no, sorry, just 11 is the dot product. Okay, how many guys got 11 for the dot product? Okay, I think it's 11, isn't it? Okay, good. Then the dot product has to be equal to the absolute value of, which means the magnitude of R, which was, we already said that, it was 3. It says it right there. And then the absolute value of J, which is the magnitude of J, which is 9, 4, and 1 makes that square root of 14, is cosine theta, and then I just have to divide both sides by 3 root 14, and then I take the inverse cosine of that. I think it came out to 11. Do I remember that right? 11.4-ish degrees. Raise your hand if you guys got that. Okay, good. Now, that involved two things. That involved you guys knowing how to figure out this, knowing that that could have actually been two different directions. One could have been negative, one could have been positive. Now, what do you have to do for today? For today, you have to picture in your head what we're doing here. Imagine these two vectors. I got two rulers for those of you at home. Imagine that they cross. Okay, that I got two vector equations that are going to intersect, and they want to know where are they going to intersect. And the more advanced thing is, are they intersecting at the same time? That happens a lot in the real world. Let's just think about that. As you walk through this doorway here, I betcha over probably in the neighborhood of 1 million people have walked through this doorway. Would you agree that they were in the same space as each other, but just not at the same time? Do you get what I'm saying? And it'll even be more magnified if we pick the doorway to the school. It's used a lot, right? Like the west entrance, for instance. I bet you at least 1/3 of our students come through that door every single day, which would be 1,000 people on the way in and 1,000 people on the way out. Okay, but there is multiple doorways in that area, so But if you just do a couple thousand a day for a doorway, or how about like the Metrodome? There's a bunch of entrances to the Metrodome. So anyway, you could figure out there's a lot of places that a lot of people are in those places, but they're not there exact same time. So when you're solving today's equations, just because they intersect doesn't mean the two rays would actually, vectors would actually hit each other, because they might be there at different times. What controls the time? In this equation, tell me what controls the time in that equation. Lambda. Lambda controls the time. At time 0, where is this vector? 1, 2, 3. Over 1, up 2, back 3. In this room, that pink ball is somewhere in the neighborhood of it. Maybe that's 1, 2, 4 or something, but it's kind of close. And again, that's where this vector is starting. And then, from that pink ball, where does it go? 2 to the right, up 1, and back 4. So 2 to the right, up 1, back 4 is like that way. So this is the vector that's kind of going that way. I can't quite reach it, but okay, I think you get the idea. Now, here's the question. Where is this vector at different times? This is a weird thought, but at time 0, do you get it's only at one spot? It's at 1, 2, 3. It's got magnitude and velocity. It's like a plane. It starts at this place, and it's not like a constant arrow that's like always there. It's a thing that's chugging along from this point to, not this point, that's the directions it's going to. Would you please figure out a few places that this plane goes? At time, we're going to do an XYZ chart, except it's going to be a TXYZ chart, or in this case, a lambda XYZ chart. And it's really easy when lambda is 0. Would you please tell me where lambda is 1 and lambda is 2? Where is this plane on its route from the starting place in the direction that it says? Okay? Figure out a few spots where this plane is. Okay, let's see if you got the right places. My dice of destiny. We're destined to be hard to find today. Roll 5, last person. What'd you get? 3 points. Say them loud and clear. X, Y, Z. All right. Now, do you guys realize this could be also I, J, and K? Okay, but we are using X, Y, and Z. Why? Because when we transport them into being parametrics, it'll be easier. All right. So, next one. Mr. CS, what did you guys get for the next point?
3, negative.
Can you guys verify that? Raise your hand if you did. Okay, good. And then the last one, Dice of Destiny, it's row 1, last person. 4, 4, what? Sorry, I can't hear you because that door's open. Could you shut that door, please? And there's a lot of hallway noise. 5, 4, what? -5. Can you guys verify 5, 4, -5, okay? Okay, good. So then, the question would be, if we had another equation that was just like that and you made another chart just like that, what if they both went through the point 1, 2, 3, but they did it at different times? Then would there be a collision? No. But would they go through the same point? Yes. That happens a lot in this class. Okay, so just be aware, a lot of times it'll go through the same point, and one kid will say, yeah, they intersect, and the other kid will say, no, they don't, because they go through the same point at a different time. And the kid that's being careful with the time piece is the one who's got it right. Because a lot of times we'll have them intersect. Now, I want you to think about, in the real world, if these two are on the ground, these two roads, they're rulers, okay? Do you get, if I just lay them down in a random fashion, they're probably going to intersect at some point. Because what's the only way that they wouldn't intersect? They're parallel. But if I put them in 3D, it goes the other way. Before, they almost always intersected. Now, think about this. With these two, if I just put this up in a random way, do they intersect? How about now? But now? Do you get what I'm saying? There's a gajillion ways that they don't intersect. There's really only one way that they do. See what I mean? It's kind of the opposite of the old days where most of the time they intersected. Now, they almost never intersect. But if they do, not only do they have to intersect, they have to also, because they're not just a stick, they are something going from here to here, like a plane, flying from this start point to this end point at a certain rate. Then they have to not only be in the same spot, but at the same time. All right, so how do you actually do that? Well, I'm going to give you 2 equations, and I want you to not overthink this too much. Why do you know that this and this intersect? Yes. They have the same starting point. Now think about this. If they have the same starting point, can they ever intersect again? If they were curves, they could. But if they're straight lines, no, if they start at the same point, they can't ever intersect there again. How could I move it so that it goes through the same intersection point of 2, 3, 4, but at different times? Change the starting point for one of them. what could she change the starting point for one of them to so that it would still go 3, 2, 3, 4, but let's say it's this one needs to change. Well, we want it to go through 2, 3, 4. How could we force it to go through 2, 3, 4 by changing it and not having the same starting point? Yes, sir. Okay, he said -2, 4, and -3. Now, how did you do that? What did you do? Oh, you made lambda, or that guy, -1. And you figured out from where? From the point 2, 3, 4? Okay. So, you basically said you like moved it back in time by having t as -1. It's a way to think of it. And now, how do I know that, are you saying that the way I have written this equation right now, it will go through the point 2, 3, 4? All right. How can I check that and see if he's really right? So, let's put in +1 and see what we get. What's that? Plus 1 times 4. 2. What's this? Plus 1 times -1. 3. You get what I'm saying? Okay, so we know it goes to the point 2, 3, 4. Okay, so cool. We know, we've established that these two equations intersect at the point 2, 3, 4. Now the question is, do they go through it at the same time? And here's how you would prove this. So imagine that this is our problem. They wouldn't tell you, like, hey, by the way, this intersects. Okay, and it intersects at this point. You have to figure that out. So here's how you do it. All right, so first of all, this generates, now this is going to be a big, long, complicated question. So pay attention closely, and if I were you, I would take really good notes on this, because this is the hardest thing you learn. And it's also, think about it, the bowling ball lab, where you're going to be rolling a bowling ball. Do you get that we want the bowling balls to be in the same place and at the same time? So this is how you do the bowling ball lab. It's exactly like this. So pay especially good attention today. All right. Next, I'm going to take and write equations for this. In fact, I know you can do this. Would you please make parametric equations for the top one and the bottom one? Like, I'll get you started. X equals -2 plus 4 lambda. That's your first of the parametric equations. And maybe since you guys have color ability, make them 2 different colors. On the bottom level here, I have x equals 2 plus 1t, or just t. Make all the parametrics that you can, and I will pause for a second while you do that. Okay, here's what you should have had. Y equals 4 minus 1 lambda, and z equals -3 plus 7 lambda. All right, on the other one, I'm going to make them in red. Y equals 3 minus 4t, and z equals 4 plus 3t. All right. That, so far, is nothing new. And by the way, if I wanted to, on a test, I could say, now, make them Cartesian. But I'm not going to do that, because you'll lose something if you do. What do you lose if you make them Cartesian? You solve them all for t, or lambda, and you get what? You get an equation that has no what? It has no time anymore. Just to clarify, this one, to solve it for t, I would get x minus 2 equals t. This one, I would get y minus 3 divided by -4. And then I just set them all equal, and they don't have t anymore. They don't have time. So I'd have information that all of a sudden lost its time variable. We need that to be able to do this part. So we are not going to take the next step and move it to, what's the next kind called? Cartesian. We're not going to do that. What we are going to do is, would you agree that if we want to know if these guys intersect, then wouldn't this point xyz be the same as this point xyz? And therefore, wouldn't their x's have to be the same? As in, wouldn't that have to equal that? That's an equation. Write that out. And this has to equal that. Write that out. You'll have a system of 3 equations and 3 variables. You are in honors pre-calc. That's why it's 3 equations and 3 variables. If you were just in regular, well, first of all, they don't do vectors, but you would be expected more along the lines of solving 2 equations and 2 variables. So it's like the difficulty level stepped up. We have 3 variables and 3 equations.
Yeah, no.
Good point. We now, when we're done with this one, we are going to have 3 equations and 2 variables. And so it's like, wouldn't I even not need that 3rd variable? But you do. In other words, some people would say, all you need is that blue one, this one I circled right here, these 2, and these 2 is all you really need, because I can solve it from there. But here's the thing. If it doesn't also work in this 3rd equation, do you get that my 3rd dimension would be off? So in other words, if it doesn't also work in here and here, then their z is messed up. If their z is not the same, can they be in the same spot? That'd be like this and this. Nope, this and this. There we go. These 2. In the classroom, I'm holding up 2 rulers again and showing them ones that have different z's. And if their z's are different, do you get they won't actually touch? And I need the z's to be in that equation. So I can't just ignore that 3rd equation. All right, this does get to be pretty intense stuff. All right, did you solve this and get t? If you haven't already, I'll show you what you do. -2 plus 4 lambda equaled 2 plus 1t. And then the next equation, I'm doing the green one now, is 4 minus a lambda is equal to 3 minus 4t. All I really need is these 2, but it better work in that 3rd equation. Otherwise, I know it didn't really work. All right, so I'm going to solve this one for t, because that's pretty easy. I'm going to subtract 2 from both sides. Taking the top equation and subtracting 2 from both sides. And that will give me 4 lambda is equal to t. Cool, that's pretty easy. Oh, did I do that wrong? Oh, it's -4. Sorry, -4 plus 4 lambda. There you go. Good, thank you. Okay, and now I could solve this other one for t, or I could plug this in for the t. Either way would work. I'm going to try that way. 4 minus lambda is equal to 3 minus 4 times the t, which is -4 plus 4 lambda. Do you get I only have lambdas left? Has anybody already solved that and has an answer for lambda? What did you guys get? Can anybody else verify that lambda is 1? All right, we will double check that just because I get a lot of people saying, huh? -4 times -4 is positive 16. And then this times this is negative 16 lambda. Now I'm going to add a lambda to both sides because I got lambdas on both sides. Plus a lambda plus a lambda. 4 equals 3 plus 16 is 19 minus 15 lambda. Wrote my lambda wrong. I'm going to subtract 19 from both sides. Negative 15 equals positive. I think there was 2 negatives in that. Let me double check that. Nope. It's just 1 negative, sorry. Lambda. Divide by negative 15 on both sides, and you were right. You got it just way quicker than other people. Lambda is 1. What does that mean? Well, first of all, it doesn't mean anything unless I can put it into that third equation and make it work. So I'm going to go back up and look at my third equation and see if 1 works in it. If I put a 1 here. And, oh, wait. I got to find the t first. Wait, sorry. I found lambda is 1. If lambda is 1, then I got to go back up and solve if lambda is 1 in this equation right here. If lambda is 1, 4 minus 1 is 3 equals, I'm just doing this equation right here. 4 minus 1 is 3 equals 3 minus 4t. And I subtract 3 from both sides, and I get 0 equals negative 4t. T must equal 0. Does it seem believable that t would equal 0? I just solved for lambda, and I got lambda equals 1 and t equals 0. Does that seem believable? Considering how you made that other point, it makes sense. You just moved it over 1 time notch. So it makes sense that one of them would be at time 1 and the other would be at time 0. Okay, but we still haven't answered where did they intersect. Here's the easy part. Finally, an easy part. If t equals 0 and lambda equals 1, if t equals 0 and lambda equals 1, I can put that in here, t equals 0 in my original equation, and lambda equals 1 in my original equation, and that'll tell me the spot where they intersect, and they'll come out the same. What is negative 2? These are all 1 times, right? So what's negative 2 plus the 4? 2. What's 5 and a minus 1? 3. Negative 3 and 7? 4. It's at the spot 2, 3, 4 is where they intersected. All right. One more thing. Because this had 3 dimensions, I need to check it in that third equation, and does it really work in the third equation is important. So I'm going to put in lambda is 1, and let me make sure of that again. Lambda is 1, and t is 0. In this third equation, lambda is 1, and t is 0, and I have 4 equals 4. Thank heavens it worked in that last equation. Otherwise, I would have solved something that wasn't really true. Okay, I know that was super intense, but let me back up a step and say, if you have 2 equations, you will not be able to tell just by looking at them whether or not they intersect. If I say, does this intersect with this? Unless I make it really obvious and make the starting point the same, then you'll be able to tell that they intersect. Okay, but and oh, I need a different thing instead of lambda. I need like a t. You can't just tell by looking at those 2 that they don't intersect. Unless you actually graph them and go, oh, I can see where these vectors are. They'll never hit because they're like this. They're askew, you could call them. Okay, but how do you tell? What was the first thing we did? This is a summary now, so pay attention. When you get this kind of a problem, what's the first thing we did? Parametrics. Once we wrote parametrics, we set what equal to each other? The x's were equal to the x's, the y's were equal to the y's, the z's were equal to z's, and then we solved it and we figured out time equals 2 and time equals 3 or whatever. In this case, we found 1 and 2, or 0 and 1 is what it was. But we found the times. What if they don't ask you for the times? What if they ask you, where did they intersect? You stick the times back in. Where would the times go? Let's say I found out it was 2 and 3. Put a 2 here and put a 3 here. And they better come out to the same what? The same point. But if they're at times 2 and 3, they are at the same point but at different what? Times. If the times are different, then they're there at different times. And therefore, just like you walking through the door, you'll go through that door today, but you won't be there at the same time as anybody else is. Okay, good. That's an overall summary. Now, I know that was tough stuff. Don't worry, the test isn't tomorrow and it's not the next day. You got some time. All right, so let's do one more like this right now together. And I'm going to find that page in the homework. Okay, so this is the spot. And just big picture, and I'm talking about how to do them right now, but you're going to do this first green page, all of them. Then you are going to do number 6 part B, but not F, so you can throw that out. Then you are going to skip this entire page. And then you get to this page, and this is the tough ones, the ones like we just did. I will tell you, both of these intersect. They will intersect at a point. But I'll even tell you, neither one of them intersect at the same point at the same time. Okay, so the question isn't, though, do they intersect at the same time? It's, will they both go through the same point? And the answer is yes, and you got to figure out what point they intersect at. Here and here. And 2 minutes is a joke. There's no way you could do this in 2 minutes. Maybe, if you're the genius in the room. Maybe. All right. All right, so that one we'll do tomorrow. So we're not doing that. But so in other words, up to this page, but don't do the plane problem. Okay? And we're going to do it, but not today. All right, so back up to this page. And actually, let's go to the very beginning, because a lot of people get confused on the very first one thinking that it's something really complicated. It is not. I'm going to move the right equation to right underneath this equation. All I'm doing is moving it. Because then, can you see that it is parametric? And all I need is that vector form, which goes like this. X, Y equals what comes next? 6, negative 6, plus t times, get what I'm saying? The negative 4 and the negative 2. There you go. I answered the first one for you. The second one is very much like it, but they have an R there. Get used to changing the R into, what did I say before? R is like the name. It's like Romeo is. So we don't want to name this thing. We want to have an XY there. If you haven't caught on to this yet, replace those with X over Y, and it'll make it a lot easier to write your equations. Here, they want you to take vector form. That's what this is. This is vector form. And make it into parametrics. Again, it'd be handy if there's an XY here to do that, right? That would do that on your iPad to remind yourself how that works. Okay, then that one shouldn't be too bad. This is the one where it really gets challenging. Look at number 8, part A. Okay, I'm going to start by writing out, this is an X, that's a Y, that's an X, that's a Y, and I'll have my little parametric form of these. X equals 2 lambda, and Y equals 1 plus 3 lambda. What did I do wrong? Oh, 2 plus lambda. Thank you. All right. And now, on this other one, I'll do it in green this time. X equals 1 plus mu. In case you don't know what letter that is, it's mu. 3 plus 2 mu. Focus. I'll be out of here when you're out of here, and it's soon enough. Okay. This equals this is an equation. Yes, sir? Yes, just make sure that the variable is not the same. He's saying basically, I don't like mu's. So if you want to do that, just go off to the side and let mu equal t or something, and I'm fine with that. Know what I'm saying? So, all right, so now that equals that, and this equals this. Once you've got that, you will be able to solve for mu and solve for lambda. Do that right now. You'll get two nice whole number answers. Oh, wait, one more thing. Because we're going to run out of time here eventually, we have about 13 minutes left. I'm going to put up the answer for part B because it's a decimal and therefore not real fun. You might want to write this down to keep yourself from having to look it up later. They do intersect when lambda is -8/3 and mu is -22/3. But this top one, part A, these come out to nice whole numbers, like lambda is 4 and mu is 5 or something like that. Okay? All right. I'm going to pause for a moment. Well, you give that top one a try, and then I'll tell you what whole numbers that should have come out to for lambda and mu. Just to clarify, though, what's the question say? It wants the point of intersection. So once you figure out that, oh, lambda's 5, awesome. Now stick it in the equation and figure out what point they're going to intersect at. If you know lambda's 5, then stick a 5 here and figure out what point you get. At least this one is only two-dimensional. It makes the equations a lot easier to solve. I'll pause while you give that a try. All right, did you get an answer? Raise your hand if your group has an answer for lambda. Did you guys get? What did you get? How about that? I think 5 was one of them, wasn't it? Mu is 5, and what's lambda?
4.
Pretty sure it's 4. You should have got lambda's 4, mu is 5. Yes, I will continue this further then for you. So these two are equal, right? So I'm going to write that equation. 2 plus lambda was 1 plus mu. Then that alone can't get my answer, but I can solve for lambda. I'm going to subtract 2 from both sides. Do you get lambda is, if I put those together, mu minus 1? Okay, what I did there? The -2 and the +1 to go together. So lambda is mu minus 1. Then I can stick that in the other equation. Here's a lambda. And I can put in mu minus 1 there. When I solve this equation now, that and that, it's a whole lot of algebra going on here, but honestly, this feels a little bit like what calculus is going to feel like. These steps aren't that hard, it's the algebra. And the same thing will happen in calculus. Calculus really isn't that complicated at all. You just do this little process, but you'll get bogged down in all the variables in the algebra. So, sorry, you need to be really good at algebra to be good at calculus. All right, when you're all done, you figure out that mu is 5. And once you know mu is 5, you can just put it there and figure out, oh, lambda's got to be 5 minus 1, so therefore if mu is 5, lambda must be 4. All right, just to clarify, I want to make sure, can anybody verify these results? I don't want to just tell you it's this. You guys got the same thing? Same, about a bunch of people did. Okay, good. All right. So make sure I didn't screw it up, which is possible. It's complicated stuff. Remember, I told you that they would intersect. So now I know the times. How do I get the actual intersection point? I take lambda is 4, and I stick it here. And that tells me 4 plus 2 is 6, comma, 12 plus 1 is 13 is where they intersected. 6, 13 is where the two vectors crossed. Did they actually collide? They crossed paths. That's different than colliding. They did not collide because at that moment, they weren't both there at the same time. They were there at different times. For one of them, it was there at time 5, and for the other one, it was there at time 4. So it was a near miss. All right, there's your homework. Have a great day.